Hey everyone, welcome to my second video. This video is going to be on variance stabilizing transformations. Let's start with an example here. So let's start with an example of a population that consists of 400 individuals. Of course, in reality, most populations are much larger than 400, but in this example, we have 400 people. So let's say we find that the correlation among all people in the population between x and y, some variable x and some variable y, is a correlation of 0.50. Okay, so our population correlation between x and y is 0.50. However, we generally don't have access to the population, so we might have to conduct a study where we take some sample from the population. So if we were to draw 20 random individuals from this population and then compute the correlation on those individuals, what we'll find is that the sample correlation doesn't exactly reflect the population correlation. So there's going to be some sampling error. So if we do this again and again and again, where we calculate a correlation of 0.59, we sample again, we calculate a correlation of 0.16, we sample again, 0.46, whatever. And you do this over and over and over again, what you can do is you can construct a sampling distribution of correlations, of sample correlations. Okay, and if the estimator, the sample estimator, is unbiased, what we'll see is that the average over all these repeated samples will be equal to our true correlation of 0.5. So this, the little dot here, denotes the average. So one thing about the correlation coefficient is that the sampling distribution greatly depends on the true correlation. So when the true correlation is 0, and remember, a correlation is bounded between -1 and 1. But when the true correlation is 0, meaning there's 0 correlation between the two variables, you see that the sampling distribution is symmetric and normal around 0. However, as the true correlation approaches 1 or -1, you'll see that the sampling variance of that distribution, the variance of that distribution, becomes smaller and smaller as it approaches 1 or -1. It also becomes a little bit more skewed. Now, the problem with this is that in meta-analysis, we tend to assume that sampling distributions and sampling errors are normal. And we also assume that in a lot of our analyses, that the sampling variance is independent of the effect size. Now, that's not always the case, and especially is not the case here. We know that the sampling variance is going to decrease as the true correlation approaches 1 or -1. Now, we can apply a variance stabilizing transformation, and variance stabilizing is denoting the fact that we want to make a transformation that forces the variance to be independent of the correlation itself, the true correlation. So for a correlation coefficient, we can stabilize the variance using a Fisher's Z transformation. Now, a Fisher's Z transformation will denote with ZR, which essentially just takes the hyperbolic arctangent of the correlation coefficient, which is this formula here. Doing this will give us a new sampling variance formula. So the sampling variance formula for a correlation coefficient uses the true correlation in it, because as, again, the true correlation approaches 1 or -1, the variance, the sampling variance of our correlation is equal to, becomes narrower and narrower as it approaches -1 and 1. So with ZR, this isn't the case. ZR, there is no true correlation in the formula. It's really only dependent on the sample size. So, and here is the sample size, which is exactly what we want. And this means that the variance for ZR is the same given a sample size for every level of ZR. So, if we go back to this example where we have a true correlation of 0, and a true correlation of 0.8, and we see that those distributions are very different for a correlation coefficient, what we find is that when we z-transform it, it becomes boundless. So instead of the correlation being -1 to 1, the z-transformed correlation goes from negative infinity to positive infinity. So it doesn't have any bounds. And also you'll notice that the sampling distributions for the z-transformed correlations are the same for both true correlations. So as the true correlation increases, the sampling variance in these two distributions stay the same. Now, the other really important thing is that these distributions are approximately normal. So not only have we been able to stabilize the variance across levels of the correlation, but we're also able to get a normally distributed sampling distribution, or approximately normally distributed. Now, correlations are not the only effect size that suffers from this unstable variance problem. We'll see that proportions and risks suffer from this, odds ratios and risk ratios, mean ratios are also known as response ratios, and variance ratios, really any ratio, and of course Pearson correlations. So if we look at the example of a risk ratios, and really any ratio, is bounded by 0 to infinity. So it has a lower bound. And as the risk ratio approaches that lower bound, that 0 value, the variance gets smaller and smaller. And also you'll notice that it is skewed positively. Now, we can do a variance stabilizing transformation by just taking the natural log of the risk ratio. And so when we take the natural log, we'll see that the distribution becomes normal and symmetric. And the other thing is that the log risk ratio is also boundless. So it can go from negative infinity to positive infinity. And notice also that a risk ratio, the null value is 1. So because the numerator and the denominator are equivalent. But the log risk ratio, the null value is 0, which pretty much allows you to say that for the directionality, negative is one direction, positive is another direction. For a risk ratio, the directionality is less than 1 is one direction, and then greater than 1 is another direction. Same thing can be true for proportions. So as proportions reach 1 or 0, those are the bounds of a proportion, the sampling variances get smaller and smaller. Where if we take a logit transform of the proportion, the sampling variance doesn't change with respect to the size of the proportion. So let's take an example for meta-analysis. So let's say we have some drug that treats some disease, and we want to test its effectiveness. Now, we allocate individuals into a treatment group and a control group. And then we want to see, after administering this drug, how many people do not have the disease anymore, and then how many people do. So what we can do is we can take a risk ratio, where we take the number of people who do not have the disease, divided by the total sample size within that group, and we take the treatment proportion of that and then divide that by the control proportion. And again, these are the proportions of people who do not have the disease after being administered the drug or the control intervention. So we can apply a variance stabilizing transformation of the risk ratio by taking the natural log of the risk ratio. And we'll see that the variance of the natural log of the risk ratio is going to be independent of the risk ratio itself. Okay, because it doesn't have a risk ratio in the formula. So if we look at this data set in R, this data set is in the metaphor package, or the metadat package. It's called dat.Wiekbauer 2021. If we preview that, we have a bunch of trials, and each trial is essentially its own study. We have a sample size in the treatment group, sample size in the control group, the number of people without the disease in the treatment group following the intervention or the drug treatment, and the number of people in the control group who do not have the disease after undergoing the control intervention. And then we also have the dosages. So for each study, they use different dosages of the drug. So we can calculate the risk ratio, the log risk ratio, by using the ESCalc function. We can put in the data set, so dat.Bauer 2021, and then we can use the measure RR. And now RR will give us the risk ratio, and in fact, RR will give us the log risk ratio. We can put in our data here, so the number of people with the or without the disease in the treatment group, number of people without the disease in the control group, and the total sample sizes within each group. And then we'll use this var.names to properly label the effect size here, which is log RR, log risk ratio, and the variance of the log risk ratio. And so what that'll do, this function adds 2 columns to the data frame that has our log risk ratio and the variance of the log risk ratio for that study. Okay. Now, if we estimate the meta-analytic model, here we just want to we want to calculate the mean log risk ratio across these studies. So using the RMA function in the metaphor package, we can put in our new data set with the new columns. We can use the log risk ratio as our outcome, and the variance of the log risk ratio as our variance, right? And then we'll use the restricted maximum likelihood method for our random effects meta-analysis. I will have a video on random effects meta-analysis, the next video actually after this. Then we can look at the model summary here. This is our estimated log risk ratio. And again, if it's above 0, then that means there's a positive effect here, and which is what we would expect. We'd expect the treatment to work. So that means that there's a higher proportion of people who do not have the disease in the treatment group than the control group. So the drug does seem to be effective, and it seems to be significantly effective if we look at the p-value here. So if we plot out the forest plot using the forest function in the metaphor package, we can input the model. We can add the header labels as well as a reference line. And this reference line for the log risk ratio will be at 0. So we see that each one of these effect sizes for each one of these studies, again, the x-axis here is the log risk ratio, but you'll find that the confidence intervals are symmetric around the sample estimate of the effect size, as well as the diamond here, which shows our mean estimate of the log risk ratio. The edges of the diamond is our confidence interval, and so you'll see that is symmetric around the middle, the point estimate as well. Now, what we want to do is, because a log risk ratio isn't very interpretable as is, we generally want to, after we meta-analyze, essentially back transform to a risk ratio. Now, we can do this with the forest function. So we put in our model, and then we add this transform argument. And now this transformation, to inverse a log, we can use the exponential function. So we'll put in the exponential function here, and that'll convert all the model statistics and all the model outcomes in the output to be in terms of the risk ratio rather than the log risk ratio. Now, it's important to note that the model itself is still being done on the log risk ratio. It's just that after the fact, when we want to interpret our results properly, we can put it back in terms of the risk ratio. So now we see that the confidence intervals are not symmetric around the point estimate within each study. So here, I mean, if you look at study 8, it exemplifies this very nicely, where we have a very short interval here between the lower bound and the point estimate, and then a very large upper bound. And that's capturing that skew of our sampling distribution in the risk ratio. So now what if we wanted to look at meta regression, or a moderator analysis of the dosage? So we can see that we can update the model in adding a moderator here using the dose. So different studies use different doses, and we expect that the treatment is more effective with a higher dose. So we can use this regplot function in the metaphor package. We can input our model after we updated the model. Add our prediction intervals. We can take out the shading. Just aesthetically, I think it looks nicer with this background. And then I made the background transparent. So when we do all that, we'll find that the dose seems to have a positive relationship with the log risk ratio. But again, when we plot this stuff out, we want to make it interpretable for the reader. So what we can do is, even though the model is estimated with the log risk ratio, we'll want to back transform all the predictions, the confidence intervals, and the prediction intervals onto a risk ratio scale. So we can use that same argument we did with the forest function and add the transformation with the exponential function, which inverses that logarithm. So when we do that, we have this nice looking curve here. And again, because we're transforming the predictions of the relationship, so even though we estimated a linear regression, essentially a linear meta regression, after our transformation, we'll see some sort of a nonlinear curve, okay, which is perfectly what we would want. So now we have it in terms of our risk ratio, which is a little bit more interpretable than our log risk ratio. And we can see that we can pretty much look at the mean effect size across different dosage levels, the mean risk ratio at different dosage levels. So that is essentially variance stabilizing in a nutshell. When we do our meta-analysis, just important to remember that we are estimating the model on the transformed values, and only after that are we back transforming the model results into the original units. So that will that essentially will allow us to, we estimate this model with normal sampling distributions, but then we want to make it interpretable, so after the fact we'll back transform into more interpretable effect size. So that's the end of this video. If you guys liked this one, give me a like, give me a subscribe maybe, and then I'll get back to you with random effects meta-analysis as my next video. Okay, see you later.